In this section, we're going to be looking at polynomial and rational inequalities. So we're going to solve polynomial inequalities, and we are going to solve rational inequalities. First, what's the definition of a polynomial inequality? A polynomial inequality is any inequality that can be put into one of these four forms. Either f of x is less than 0, or f of x is greater than 0, or f of x is less than or equal to 0, or f of x is greater than or equal to 0, where f is a polynomial function. How do we solve polynomial inequalities? The procedure for solving polynomial inequalities is as follows. The first thing you need to do is express the inequality in the form f of x is less than 0 or f of x is greater than 0. So you need to have all the terms of the polynomial on the left-hand side of the inequality and 0 on the right-hand side of the inequality. Of course, this could be less than or equal to or greater than or equal to also. The second step that you're going to use to solve polynomial inequalities is to solve the equation f of x equals 0, using whatever technique is necessary for solving that polynomial equation. This will find your boundary points. Any real number solutions to this equation will be your boundary points. Step 3, you're going to locate these boundary points that you found in step 2 on a number line. And these boundary points are going to divide your number line into intervals. Step 4, you're going to choose one representative number called a test value within each interval, and you're going to evaluate the function f at that number. So just pick any number that's in that interval, test it, and see what happens. If the value of your function is a positive number, then your function will be positive or greater than 0 for all the numbers in that interval. If the value of your the value of the function at your test value is negative, or f of x is less than 0, then it will be less than 0 for all the numbers x in that interval. The last step is to write the solution set, selecting the interval or intervals that satisfy the given inequality. The procedure is also valid if less than is replaced by less than or equal to, or greater than is replaced by greater than or equal to. However, if the inequality involves less than or equal to or greater than or equal to, you include the boundary points, the solutions of the equations in the solution set. So if you have less than or greater than, you would use parentheses on your intervals. If you have less than or equal to or greater than or equal to, you would use brackets on those boundary points. You always use parentheses if you have infinity or negative infinity on those endpoints, but on the boundary endpoints, you would use brackets. Let's do an example. We're going to solve and graph the solution set x squared minus x is greater than 20. The first step in solving any polynomial inequality is to get all the terms of the polynomial on the left-hand side of your inequality and 0 on the right. So we need to subtract 20 from both sides of this inequality. So I have x squared minus x is greater than 20. So I'm going to subtract 20 from both sides to get the polynomial on the left and 0 on the right. So now I have x squared minus x minus 20 is greater than 0. The next step is to find the boundary points. And the boundary points are these points that are going to break my number line into intervals. So I need to solve the equation f of x equals 0. So I need to solve x squared minus x minus 20 is equal to 0. And I'm going to solve that using factoring. That's the easiest way to do this. You could certainly use the quadratic formula. So I need two factors of negative 20 that when I add them, outside plus inside, I get negative 1. So that would be what? Negative 5 and positive 4. So if I were to FOIL that back out, I would get x squared plus 4x minus 5x would be minus 1x, the middle term, minus 5 times plus 4 is minus 20, the last term. All right, now I need to solve this equation by setting each factor equal to 0. So set x minus 5 equals 0 and x plus 4 equal to 0. I'm going to add 5 to that first one, both sides. I get x is 5. So there is one boundary point. Subtract 4 from both sides, and there is my second boundary point. So my two boundary points are 5 and negative 4. Okay, so the next step is I'm going to locate these boundary points on my number line, and I'm going to write my intervals. So I have what? Negative 4 is a boundary point, and 5 is a boundary point. Now my inequality was a greater than, so I'm not going to include the boundary points in the solution. So can you see how these two boundary points naturally break my number line into 3 intervals? The first interval's all the numbers to the left of negative 4. So that would be from negative infinity to negative 4. And I'm going to use parentheses because the boundary points are not included in my solution because I have a greater than, not a greater than or equal to. The next interval, can you see that it's all the numbers between negative 4 and 5? So that interval would be all the points from negative 4 to 5. And the last interval would be everything greater than positive 5. So everything to the right of 5, that would be 5 to infinity. So now I have my 3 intervals. I'm going to pick a representative value in each of these intervals and test my inequality. Okay, so I'm going to set up my intervals. I'm going to make myself a little table here. My intervals were from negative infinity to negative 4, from negative 4 to 5, and from 5 to infinity. Now I'm going to choose a test value in each of these intervals. So a test value in the interval from negative infinity to negative 4 would be any number less than negative 4, any number to the left of negative 4. So I could just choose negative 5. That would be to the left of negative 4. Then I need to choose a point between negative 4 and 5. And honestly, the easiest point to choose in that interval would be 0, because 0 would be between negative 4 and 5. So I'm going to choose 0. And then I need to choose a test value in the interval from 5 to infinity. So I need any number that's to the right of 5 would be in that interval. So perhaps I choose 6. All right, so now that I have my test values, chosen, I'm going to evaluate my function at each of these test values. So my function is f of x equals x squared minus x minus 20. So I'm going to evaluate this function at -5. And when I evaluate that function at -5, I get 10. When I evaluate this function at 0, I get -20. When I evaluate this function at 6, I get 10. So the conclusion I have here, 10 is a positive number. So for every number in the interval from -infinity to -4, the value of my function will be a positive number for all of them. So if I evaluated this function at -6, I would get a positive number. If I evaluated it at -7, it would be positive. For every value in that interval, the function will be positive. All right. For the second test point 0, I got -20. So for every point between -4 and 5, if I were to evaluate this function, I would get a negative number. So for example, if I evaluated the function at -3, it would be negative. If I evaluated it at 1, it would be negative. So for every value between -4 and 5, the value of my function will be negative. So my conclusion is that my function value would be less than 0. And since when I evaluated this at 6, I got positive 10. Again, the value of my function for every single solitary point to the right of 5 would be positive. Okay, so now we have our conclusion, and we're going to look at our original function. Our original function was x squared minus x minus 20 is greater than 0. So are there intervals for which this function is greater than 0? And the answer is yes. In the interval from -infinity to -4, the function value, when I evaluated my function, was positive. It was greater than 0. So this is true for any point between -infinity to -4. It's also true for the last interval from 5 to infinity. It is also true. So the solution to this inequality is the union of those two intervals. So the solution is from -infinity to -4 joined with 5 to infinity. Because in both of those intervals, the inequality that this function's greater than 0 or a positive number is true. All right, so what was our solution set again? It was from -infinity to -4, unioned with from 5 to infinity. And then we're going to graph this. This is all the points to the left of -4 and all the points to the right of +5. All right, what's a rational inequality? A rational inequality is any inequality that can be put into one of these forms. F of x is less than 0, f of x is greater than 0, f of x is less than or equal to 0, or f of x is greater than or equal to 0. And f is a rational function. And as you recall from the last section, what makes a function a rational function? What makes a function a rational function is that it's the ratio of two polynomial functions. So the numerator is a polynomial and the denominator is a polynomial. All right, so let's look at an example. And you follow the same steps that you follow to solve a polynomial inequality, the only difference is how you find the boundary points. So step number one is again that we have to write this inequality in the form where we have the rational inequality on the left-hand side of the inequality symbol and 0 on the right-hand side. And in this rational inequality, we have 1 on the right-hand side of this inequality. I can't solve this problem until I get that 1 over onto the left-hand side. So I need to subtract it from both sides of the equation. Inequality, excuse me. So I am going to subtract 1 from both sides. So now I have 2x over x plus 1 minus 1 greater than or equal to 0. Now, to be able to solve a rational inequality, I must have this in the form where I have a rational function on the left-hand side and 0 on the right-hand side of the inequality symbol. On the left-hand side of this inequality, I have 2 separate terms. I can't do it that way. I have to have it as a single fraction. So I have to find the least common denominator and then combine these 2 fractions. So in my case, the least common denominator, there's only one. It's x plus 1. So I must multiply the negative 1 times x plus 1 over x plus 1. All right, so now I'm going to carry out that multiplication. I have 2x over x plus 1. I have a negative here, so that's going to be minus x. Negative 1 times positive 1 is minus 1. I have to distribute that negative across all the terms in that numerator. All right, now I can combine like terms. The denominators are the same, so I can add the numerators. I have 2x minus x would give me 1x. Minus 1 over x plus 1 is greater than or equal to 0. So now I have it in the form where I have a single rational function on the left-hand side of my inequality symbol, and I have 0 on the right-hand side. So now I'm ready to proceed to find my boundary points. All right, so to find the boundary points in a rational inequality, I'm going to set the numerator equal to 0, and I'm going to set the denominator equal to 0, and that will give me the boundary points. Boundary points in a rational inequality are either x-intercepts or vertical asymptotes. To find the x-intercept, you set the numerator equal to 0. To find the asymptote, the vertical asymptote, you set the denominator equal to 0. So to find the boundary points of a rational inequality, again, you set the numerator equal to 0 and the denominator equal to 0. I'm now going to solve these 2 equations. So my 2 boundary points are positive 1 and negative 1. So now I'm going to locate my boundary points on my number line, and I'm going to set up my number line into intervals. So my 2 boundary points were negative 1 and positive 1, and I am going to write that inequality over here so that we can take a look at it. All right, so I have now these 3 intervals. I have from negative infinity to negative 1, and you'll notice that I'm not going to put a parenthesis on that negative 1 yet. We're going to talk about that for a second. Then we have from -1 to +1. And we have from 1, oops, didn't want to do that. I honestly did not want to put that negative. Let me get my eraser here. Listen to me mumble. All right, so the last interval is going to be from 1 to infinity. So now let's talk about brackets or parentheses. Looking at my rational inequality, -1, x equals -1, would be a vertical asymptote. In other words, x can't equal -1. Because if I put -1 in this inequality, I'm going to have division by 0. So I cannot have a bracket on the -1. It has to be a parentheses. -1 is not a solution to this inequality. However, the x-intercept is a solution because this inequality is greater than or equal to. The x-intercept is a solution because the x-intercept is the value for which this function is equal to 0. If I substitute 1 into this function, I get 0, and 0 is greater than or equal to 0. So I must include the boundary point 1 in my solution. All right, so now I have my 3 intervals. I'm going to repeat the process that I used to solve a polynomial inequality. I'm going to set up my intervals. I'm going to choose a test value in that interval. I'm going to evaluate this function, and then I'm going to draw a conclusion. All right, so my intervals were from -infinity to -1, from -1 to 1, and from 1 to infinity. And I'm going to choose a test value in that interval. So I'm going to choose any number that's less than -1. So -2 would be less than 1. All right, then I'm going to pick a test value between -1 and +1. Well, 0 is between -1 and +1. That would be the easiest number to pick. And then any number greater than 1 would be in the interval from 1 to infinity, so we're going to pick 2. All right, now I'm going to evaluate my function at these test values. And we had x minus 1 over x plus 1. All right, so let's evaluate this at -2. That would be -2 minus 1 over -2 plus 1. And I believe that's going to be +3. Then let's evaluate this at 0. That would be 0 minus 1 over 0 plus 1. That would be -1. Let's evaluate this at 2. We have 2 minus 1 over 2 plus 1, which would be 1/3. All right, so let's draw our conclusion. So since for the interval from -infinity to -1, the value of my function at my test value was positive, we can conclude that for every test value in that interval, so for every value to the left of -1, this function will be positive. All right, then we could look at the next interval. The next interval for our test value, our function was negative. So we conclude that for every value in that interval, if no matter what value I picked, the function value would be negative. And in the last interval, it's positive, so we're going to make the conclusion that it is positive for every value in that interval. So our original function, our original inequality was x minus 1 over x plus 1 is greater than or equal to 0. So we are interested in the interval or intervals for which, when we evaluated it for the test value, that we got a positive number. And that would be from negative infinity to negative 1 and from 1 to infinity. So our solution is from negative infinity to negative 1, union with from 1 to infinity. And again, just to remind you of our original function, our original rational function looked like this. So we have a bracket on the 1 because we have equality. And if we have equality greater than or equal to or less than or equal to, we include the boundary point that makes the numerator equal to 0. We never include the boundary point that would make the denominator equal to 0. We cannot divide by 0. So what does our graph look like? We have all the points to the left of negative 1 and all the points to the right of positive 1, including positive 1. And that concludes section 3.5. Thank you very much.